Okay, so we are going to finish off the last example from section 5.3. We're given the function f of x equal to x to the fourth power plus 1 divided by x squared. Again, we want to find where the function is increasing, where it's decreasing, as well as the local extrema. So again, first thing we want to do with this example is check the domain. This function is rational, so our denominator cannot be equal to 0, which means that x cannot be equal to 0. Okay, so we're going to need to check that once we have completed our sign chart for f prime. Okay, so we're going to go ahead and differentiate this function to find the critical points. So the derivative f prime I have to use quotient rule for. So that's low, d high, the derivative of the top function is 4x cubed, minus high, d low, the derivative of the bottom function is 2x, all over low. So when I square x squared, that's going to make x raised to the fourth power. Okay, so let's go ahead and simplify the numerator. So x squared times 4x cubed is going to make 4x to the fifth power minus, and then I'm going to distribute 2x across both terms. So that's 2x to the fifth plus 2x all over x to the fourth. And then I'm going to distribute the negative across both terms. So that makes f prime of x equal to 4x to the fifth minus 2x to the fifth minus 2x all over x to the fourth power. Okay, so when I combine like terms in the numerator, the 4x to the fifth minus 2x to the fifth is going to make 2x to the fifth minus 2x all over x to the fourth. And then I can go ahead and factor a 2x out of the numerator, which leaves me with x to the fourth power minus 1 all over x to the fourth. Now I'm going to combine two steps in one here. So I'm going to cancel a factor of x on top with a factor of x on bottom. And then x to the fourth power minus 1, I can factor that. So that's going to be the difference of two squares. So that's going to factor to x squared plus 1 times x squared minus 1. But x squared minus 1 is also the difference of two squares. So that's not factored completely. I'm going to break that down into x plus 1 times x minus 1. All over x cubed. Okay, so that right there is my derivative simplified completely. We now want to identify the critical points. So critical points are going to be where the derivative is equal to 0. So that happens when the numerator is 0. So the values that make the numerator 0 are x is equal to -1 and x is equal to 1. And our other critical point is going to be where our derivative is undefined, because my derivative is in fraction form. That's going to be undefined when the denominator is 0, which happens when x is equal to 0. Okay, so we're going to make a sign chart here for f prime. We're going to list the critical points in order from smallest to largest. And then I'm going to test the rightmost interval because it's the easiest one for me to test. Now, I don't have to bother testing that first factor, x squared plus 1, because no matter what we plug in for x, that factor is always going to be positive. Okay, so our sign is going to be dependent on these three factors, x plus 1, x minus 1, and x cubed. So if I pick a value bigger than 1, let's say I pick 2, this factor on top will be positive, this factor on top will be positive, and the factor on bottom is positive. So we have a positive numerator divided by a positive denominator. So that first interval from 1 to infinity is going to be positive. And then I'm going to use the multiplicity of the zeros in the numerator and denominator to determine the signs on the other intervals. Okay, so each of those zeros has a multiplicity that is odd, which means the graph, or which means the sign will change on the neighboring intervals. So this interval here will be minus, that interval will be plus, and that interval will be minus. All right, so once we have our sign chart, we can go ahead and determine where the function is increasing and where it's decreasing. So our function is increasing where the derivative is greater than 0. So that happens on the open interval from -1 to 0, union the interval from 1 to infinity. Our function is decreasing where f prime is negative, so that happens on the interval from negative infinity to negative 1, union 0 to 1. Okay, so we want to do the local extrema, so our local max and the local min. Now, when we look at our number line or our sign chart, we see that f prime changes sign from positive to negative at 0. Okay, so at first glance, you would think, okay, the function has a local max at x is equal to 0. But when we go back and check that against our domain, our function is not defined at 0. Okay, so we can't have a local max at a value that is not in the domain of our function. Okay, so that means that our function here has no local max. And then if we want to find local mins, we are looking for where the derivative changes sign from negative to positive. So the derivative changes sign from negative to positive at negative 1 and also at 1. So it looks like we have two local mins. First one is at negative 1 comma something. The second point is at 1 comma something. So all we want to do is plug negative 1 and 1 back into our original function. And when we plug negative 1 and 1 in, we're going to get the same output either way. So when we take negative 1 or 1 and raise it to the fourth power, the output's going to be 1. So the numerator is 1 plus 1, which is 2. And the denominator, whether we plug in negative 1 or 1, whenever we square that, the output is 1. So 2 divided by 1 is 2. So that's going to make the y coordinates for both of these points here, 2. Okay, so this is why we have to check the domain at the very start for problems for which we are trying to find local extrema, because the sign chart can be misleading. Again, at first glance, it looks like the function will have a local max at 0, but that point is not in the domain of our function, therefore not making it on the graph of our function. Okay, so we can't have a local max or a local min for that matter where the function is undefined. Okay, so that's it. That wraps up the lesson from 5.3, and you guys should be able to go through and complete your homework assignment now. So hope you guys are doing well, and we'll see you all in class either on Wednesday or Friday. All right, take care. Bye-bye.